Chapter 12, Deflection of Beams and Shafts, Part B, Example number 7. So let's see, what do we have in this example? So if we want to calculate delta maximum at the cantilever beam at the free end of B with a non-uniform distributed load which is varying from 0 to W from the beginning of the beam to the all the way to the right to the free end of B. So we want to calculate the maximum deflection which happens at B. That's delta maximum. Hmm. Let's see how we can solve the problem. So just assume we can cut the beam through by a length of x, which you can easily see here. That's a length of x. And at the same time, you do know for such loading, if you just convert this by a half of WL, at the location of a 1/3 of L, a sigma m at fixed end is WL squared over 3EI. And RA is definitely a half WL. So RA is WL over 2. And let's see, that's RA. And let's see what do we have for moment at a distance of x. So one can say when it was a whole length, it was the intensity was W of the load in distributed load. Now, if it's X, what is that? By a simple comparison between them, you can see a X is or the question mark is W times X over, so that's X times W over L. X over L times W is the intensity of the distributed load at the very end point of uh, travel farther to the right of x, and that located at 1/3 from base. That's 1/3 of x. And the if you convert the distributed load to concentrated load, that's a half of the area. That's the half of intensity. That's half of x over L times W times the length itself, which is x. That's a half of x over L times Wx. Mhm. Then what if we just develop the moment about the point x? Uh-huh. If we develop the moment for x that says sigma mx is equal to a mx positive with consistent with the direction of movement plus a the distributed load converted to concentrated, which is a half of x over L times Wx times the distance, which is 1 over third. So that's 1 over third. So that a half of x over L Wx times 1/3 of x. That's a 1 over 2x over L Wx times 1/3 of x minus Ra times x minus Ra, which is WL over 2, times x, which is a negative a 1/3 of WL, WL squared. And that's a equation for mx. If you derive the equation for mx for 2y's, it just gives you the delta, and we are looking for delta maximum. So then by having moment equation, you can easily get the equation for theta by a constant developed C1, and the other one is Y deflection equation, which includes both C1 and C2. So if we consider the first equation like equation number 1 and Y equation number 2, And at the same time, we do know at x equal to 0, at x equal to 0, both y is equal to 0 and y is equal to 0. So then a and 1, a and 1 at x equal to 0, the theta is equal to 0 gives you c1 equal to 0, and b and 2 give you c2 equal to 0. If both of the constant goes 0, so then we can easily have the equation of y based on something like there is no y. This is 0, this is 0, we just get them equal to 0. And we do know that from the geometry, we do know delta max happens at the very end of the beam, so that's x equal to L. And delta maximum, if you replace the numeric value, it's a negative 11 over 112 WL4 to the 4 over EI. And that's almost a 1 over 12. 1 over 1 over 12 WL to the 4 over EI. And again, if you have a cantilever beam handling a non-uniform distributed load varying from 0 to W, your maximum deflection happened at the free end B by the amount of a negative 11 over 1 over 20, 120 WL. Uh, uh, let's verify that. Yes, please modify this part. That's WL to the power of 4. That's a to the power of what? Of WL 4 over 120 EI. Thank you.